Hello, everybody, and welcome to this session on Civil Engineering and Renewable Energy 1. Next we have Mr. Jiahao Wei, also from University College Dublin. So Jiahao, if you want to turn on your camera, great. And you can unmute yourself and you can also share your screen.
Okay, thanks.
So please start when you're ready. And everybody keep the good questions coming in.
Okay, thank you. Hello, everyone. My name is Jiahao Wei, a first-year PhD in UCD. It's really honored to be here to present and listen to many great presentations from other speakers about what they have done with OpenFOAM. I used to use Fluent as the main software to perform my research during my postgraduate time. So this study was done by Fluent, and I have to say I'm an OpenFOAmer now as well. Okay, now I will make a start. This study is concerned about the optimization of oxidation ditch. Oxidation ditch is one of the most common reactors in wastewater treatment industry, which are large, round, or oval ditches used for the aerobic and anaerobic treatment of wastewater. This figure shows the structures of the oxidation ditch from the top view and the flow direction. Some impellers are around the bends to push the water flow, and one or more horizontal aerators guarantee oxygen supply. In practice, oxygen ditch is prone to sludge accumulation in partial due to the low velocity at the bottom. Then a lower hydraulic efficiency will cause a bad quality effluent. And since the water flow is driven by the impellers, so the size of impellers is crucial to the whole system. Then CFD is a relatively cheap and time-saving way to obtain the complex hydraulic characteristics of the reactor, and also can be used for the design of oxidation ditch, the optimization of structure, and so on, which is of great significance for the stable operation of oxidation ditch and the improvement of treatment efficiency. Here are three main contents of this study, including dimensional analysis, simulation, and the energy efficiency analysis. Dimensional analysis is a method to deduce the relationship between physical quantities by utilizing the regularity of dimensions. For example, if we know v velocity is a function of r, rho, g, etc., but we don't know the specific relationship between them, then dimensional analysis can be applied to the variables to find a set of pi parameters, which is a set of dimensionless numbers. In this case, r, rho, and g are selected as basic physical quantities because they are independent of each other. And this means other parameters like viscosity can be expressed by the dimensions of these three basic physical quantities. More specifically, the dimensions of the physical quantities are written in the dimensions of length L, time t, and mass m. The exponents of each dimension must be the same on both sides of the equations. So the following equations can be obtained, and then through deduction, the equation 6 is the relationship between the average velocity over a cross-section V and the radius size of impellers R, in which the coefficient can be determined by CFD or experiments. Then its simulation part. The time averaged, mass, and momentum conservation equations can be written respectively like this. As we know, the Reynolds average Navier-Stokes equations can be always closed by the principal turbulence models, such as the standard K-epsilon model and the relatively improved models called renormalization group and realizable K-epsilon models in popular CFD. In this study, the RNG K-epsilon model is selected as turbulence model because compared with the standard model, RNG model considers the influence of vortex on turbulence, which improves the accuracy of vortex flow. The figure 1 shows the details of the calculation region and size information. 3 impellers are installed at both ends of the oxidation ditch. The 3D meshes and the 2D horizontal plane meshes for the computational domain are shown in figure 2. And the geometry and mesh are generated by the software Gambit. Figure 3 shows the shape information mesh of impellers. Then, in order to meet the simulation requirement, two different kinds of mesh are computed respectively under the same initial and boundary conditions. Figure 4 shows the comparison of the velocity component in x direction along the vertical line at the sampling point, which shows a good agreement and validates that the computational grid with 172,640 meshes is an independent one. Here is the initial and boundary conditions. There's one thing should be noted is that since this study considers the influence of single factor radial size r on the average velocity of cross-section, the rotation speed of impellers is set as a fixed value, 3.14 radian per second. This is the simulated velocity fields and streamlines on the horizontal plane under 5 different radial sizes of impellers. As can be seen from figure 5, when water flows into a straight channel, the recirculation zone is formed at the inner side of the straight channel because of the uneven flow velocity. The recirculation zone gradually increases with the increasing of the radial size of impellers, which is mainly because with a constant rotation speed, the larger radial size will result in a further uneven velocity distribution at the bend outlets, which leads to a further larger recirculation zone. Therefore, with a constant rotation speed, the radial size of impellers can be neither too larger nor too smaller. Larger radial size will cause larger recirculation zone, which affects the effective volume of oxidation ditch. Smaller radial will cause the velocity not to meet its requirement, so that large accumulation is formed. Then, according to the results of dimensional analysis and simulation data, which is shown in table 1, the fitting line can be calculated, which is equation 8. And then the best radial size can be found. So the radial size of 1.53 meters can achieve the required minor sectional average velocity, 0.3 meters per second, which is required for oxidation ditch design. This is the calculation method of energy efficiency. And then substitute the data in table 2 into the equation 9 and 10. The energy difference E and energy efficiency P can be obtained. As can be seen in the figure 7, the lengths of the channel from section 2 to 5 and 6 to 3 are almost the same and are about half of that from section 4 to 1, which causes that the water head loss from section 4 to 1 is much bigger than those from section 2 to 5 and 6 to 3. Therefore, the energy efficiency for impeller 1 is the biggest, and those for impellers 2 and 3 are nearly the same. The smaller and smaller than that of impellers 1. The analysis of the energy efficiency for each impeller at a fixed flow speed shows that the energy efficiency was much affected by the energy loss of the open channel flow from the downstream of the impeller to next impeller. This is the main conclusions. And next, as the rotation speed is also a dominant factor for the cross-sectional average velocity, so I will do a sensitive analysis of rotation speed and radial size of impellers and consider the influence of these two factors on the cross-sectional average velocity at the same time. Thank you for your attention. Any questions?
Great, thanks very much, Jiahao, for a very nice talk. So I don't see any questions in the chat at the moment. We're still chatting about Yushang's, but I definitely have some questions. So maybe people might want to ask questions in the chat while I'm asking some questions. So at the moment, these results are from Fluent, are they, Jiahao?
Yeah, they're from Fluent.
So you said you are wanting to go to OpenFOAM. For this particular case, will you use, is it your plan to use OpenFOAM?
You mean the further plan?
Yeah.
Yes, I'm studying OpenFOAM now, and I prefer use OpenFOAM in the future.
Okay. Why? What benefit do you think OpenFOAM will bring to this or these analyses?
The setting in OpenFOAM is more flexible than commercial software Fluent, I think. And it has more solver and the settings in the OpenFOAM can be more flexible, I think. Yeah.
Okay. And for your particular case, was it moving mesh? Were the propellers were moving mesh, were they, or they really
yes,
they weren't
moving mesh.
It's really moving mesh. Okay. How many cells did you have in your entire domain?
The cells, the total is 172,640 meshes.
Okay, we have a question now in the Q&A. Thank you for your presentation. Which solver of OpenFOAM do you think would work for your case?
Because I'm a newcomer.
Sure.
Of OpenFOAM, so I don't know.
Sure. This is a you solve this as a steady state analysis, do you? This is a
yes, it's unsteady.
It's unsteady, is it?
Incompressible.
It's steady or unsteady?
Unsteady.
Unsteady. Okay, so you really solve it transiently in time. So then maybe something like pimple foam or piezo foam or something. So this is a sludge. It's not just water. So there's solid particles in this liquid.
No,
as well.
it's in this case it's a single phase. It's a single phase simulation. But in reality, in the oxidation stage, there's water, solid, and air. It's a more complex situation. Sure. So I plan to do a two-phase flow in the future.
Sure.
In the next research.
So I have two questions, one in the chat. Does the study include sludge height?
Sorry?
Does the study include sludge height? Do you account for sludge height in some way?
No.
Okay. Short and sweet. I guess so. You're modeling it as single phase at the moment. So you're treating air, water, and solids as one. So I guess that sounds like a maybe an important next step. And then maybe one of the last ones from Joseph. How did you model the viscosity?
Viscosity is I think it's
Is it Newtonian? Do you just take a constant value for viscosity, or do you have a non-Newtonian law?
Can I post it in the,
yeah, that's fine. So you can follow up in the chat. I'm not sure. I think you may be able to answer directly in the Q&A section, but you can answer in the chat anyway. So that's perfect. Okay, that's great. Thanks very much, Jiahao, and thanks for the presentation and the discussion afterwards. So you can stop your video now, and then we'll hand it over to Salvador next. So Salvador, you're going to talk about pedestrian wind comfort. So you can share your screen, and you can go ahead whenever you're ready. And if people are struggling to find the Q&A, it should be on the right-hand side. You have session information. And then there's live Q&A and then discussion forums. So there's a little arrow. If you press the arrow on the right hand side, it drops down a little Q&A section. But it's fine to put them in the chat as well. Okay, go ahead.
Okay, so you should be able to see the screen now, yeah? Okay. Good afternoon. My name is Salvatore Renda. I'm Senior CFD Engineer at Engis, and I'm here to talk to you about an efficient framework for pedestrian wind comfort assessment in Helix core. Pedestrian wind comfort is one of the most common applications in the architectural engineering and construction industry. High-rise buildings induce winds at ground, which may impact on human activities. And in order to obtain planning permissions for new buildings, often wind comfort studies are required to assess feasibility of the development. Wind studies are computationally very intensive, as many wind directions and scenarios have to be solved, and the data have to be aggregated together and combined with the weather data. In 2019, City of London RWDI published the standardized methodology for London based on 36 wind direction analysis. And wind consultants have developed their own workflow, often combining CFD runs results using Bash and Python scripting. In this talk, I'm going to introduce a new system in Helix which simplify and speed up the wind comfort assessment. The framework that we propose removes the need for external scripting, but is still open source. Therefore, it enables the specialists into the field to add value and customize the field based on what they want to do. How do we do this? The Engis recipe consists of two key ingredients. The first ingredient is a multi-instance framework, which is mainly used to simplify and streamline the workflow. What is it? It's a system for workflow automation and efficient asset reuse. It allows to run design of experiments analysis, such as geometry and boundary conditions variations, without the need for external scripting. And what does it do? It reuses meshes and settings for multiple concurrent or sequential solutions. It enables to run case variations, and it enables to combine results for multiple solutions. How does it do this? It splits the mesh and solution solver database, and with an outer instance loop around the time loop. A typical standard solver framework is single mesh, single solution, or in case we consider a CHT case, is multi-mesh, multi-solution. The multi-instance framework allows all of the above, but also single mesh, multi-solution, multi-mesh, multi-solution, and sequential process automation. For example, solution obtained sequentially one after the other one. And this is what is done, for example, in the case of the wind comfort study. Or concurrent process automation. For example, we use this for the multi-point join, mesh and solutions run concurrently. And after that, sequential process automation with concurrent process coupling. We use this for the transient multi-point join, so we can go from here to here. The second key ingredient of our recipe is a block-coupled solver. Flow equations in CFD can be solved in two different ways, in segregated or coupled way. Segregated solvers solve the equations subsequentially, so one after the other one. The terms are explicit coupled, and there is relaxation. All those things tend to slow down the convergence. Coupled solver algorithms solve the PU system equation simultaneously, so all together. Terms are treated implicitly, and there is no relaxation. Therefore, coupled algorithms are generally faster to converge than segregated one. The proposed methodology is based on a new pressure velocity block coupled solver with an algebraic multi-grid to solve the linear system matrix. This framework is compatible with the existing segregated structures such as FV options, boundary conditions, and interfaces. is backward compatible with segregated system and I/O, and the speed up is between 2 and 5 times faster with respect to a segregated solver based on the size of the mesh and the type of application. The wind comfort assessment is done by combining local velocities from multiple wind directions along with climate data. Weather data are generally represented as wind rows and are given in the form of variable distributions. The CFD is solved for multiple wind directions, usually 36, and total probability of exceedance is calculated for each velocity threshold given by the comfort criteria. After that, exceedance probabilities are combined together based on the comfort criteria to obtain comfort plots. The comfort plots tells the suitability of an area based on the wind condition, so the activity suggested for each area. Results for multiple wind directions are combined together to generate a total probability of exceedance fields and comfort criteria by means of a multi-instance aware function object. The volumetric probability of exceedance, volumetrics, is calculated according to this form. This is a question here. P is the total probability of exceeding the U limb given by the criteria, and there is a sum all over the wind directions, and P, C, and K are variable distributions parameters, and R is the so-called speed ratio, is the ratio between the local velocity and the reference velocity. There is some correction in this form or in other forms, which takes into account turbulent gust winds. Different comfort criteria can be chosen, like Lossan, Davenport, and NIEN 8100. To prove the capability of our simulation framework, we use the Niigata case from Architectural Institute of Japan. Niigata is an urban area in Japan consisting of mainly low-rise buildings. The study assessed the feasibility of 3 high mid-rise buildings. For this case, the velocities are available at 80 probes from the wind tunnel for a scaled model. GUI is a mesh consisting of 26 million cells and incompressible steady-state runs set up with realizable K-epsilon model, which is generally the standard in the industry. We compare 2 solver algorithms, the segregated solver, which basically runs simple form, and Helix coupled. For simple form, we use simplex settings and quite aggressive relaxation factor, so it's quite tuned. And in terms of boundary conditions, we fix velocity and turbulence profiles on the sides of the domain and the fixed mean pressure at the top. And now let's have a look at the results. This slide presents shows the accuracy. CFD experiments, CFD versus experiments correlation plots of the wind speed ratios given by local velocity divided by reference velocity at the 80 measurements point are presented for 4 wind directions. We also present here the R-squared factor, which tells how well the CFD correlates with the experiments. The closer this value is to 1, the better the CFD matches the experiments. The plots tell us 2 things. The first thing is that segregated and coupled solver solutions are pretty much consistent, are almost overlapping. And the second one is that we see a good correlation because with the experiments, because their squared factor is around 0.9. Next slide, we look at the convergence and at the CPU time for 16 wind directions. To make a fair comparison of the convergence, we use an objective convergence assessment on aggregated data from the 80 probes in the model. So we compare so that we can judge the convergence at the same way for segregated and coupled solver. The total CPU time to reach the convergence for the segregated solver is 4.12 hours, and for the coupled one is 2.13. This results in a speed up of 1.93 and a CPU saving of 47.4. Not only the coupled solver converges faster, but if we look at this graph here, we can say that it also improves the convergence of the solution because the solution is less oscillatory. Here you can see that the segregated solver in gray is oscillating. So if you would have to take the results, you would need to run like longer for several hundred iterations and average them. And this slide presents the comfort criteria. The total probability of exceedance is displayed here for velocity thresholds from the criteria, and those are combined together in this plot here, which is the Lossan criteria. The Lossan criteria tells that areas highlighted here in blue are suitable for frequent sitting, in light blue for occasional sitting, green for standing, orange for walking, and finally red means uncomfortable for human normal activity. Some take-home messages. We have showed the capability of our multi-instance framework in conjunction with the coupled solver algorithm. The multi-instance framework is ideal for type of analysis which take advantage of automatic workflow. Everything is like a design of experiment analysis or similar. So it can also apply to other type of analysis. The pedestrian comfort is just specifications, and it removes the need for external scripting. The pressure velocity block coupled solver was shown to be, for this specific application and these mesh sides, 2 times faster to reach the convergence than the segregated one, whilst the accuracy of the solution is preserved. If we assume a cost of 10 pence per core hour, extrapolating at 36 wind direction, which is the typical size of the wind study on a 26 million cells mesh, this would result in a cost reduction of £60 per scenario. Any questions? And here I put my contact details. And thanks for your attention.
Great. Thanks very much, Salvatore, for a very interesting talk. So if people have questions, just put them in the chat or in the Q&A section. So I've got lots of questions that I'll start with while people are typing questions. Why are the results slightly different for the block coupled solver versus the segregated solver? Why are they not exactly the same?
It depends from the level of convergence that you achieve. The structure of the solver is the same. The structure, the underlying let's say boundary conditions and so on. It's just that the coupled solver converges better. And I actually haven't put into this presentation, but I have another slide where the result. I have some other way of plotting the results, where I plot basically the probes and the wind speed ratio in another form. And there you can see that, for example, there are points into the wake of the buildings where the solution is more different. And this makes sense because you know that there are issues. There is a transient behavior in the wake of the building. So you may see this effect more accentuated.
Okay, so if you were to converge the segregated and block coupled solutions to a very tight tolerance on a fine mesh, would the difference start to disappear, would it? Or maybe this transient nature just gets amplified in the segregated and coupled?
This depends. The block coupled solver converges better, but it's not like a miracle to
sure.
stationarize like flows. If the flow is transient, at some point you have to solve the unsteadiness of the flow.
Sure. In this industry, it would be uncommon to solve transient problems, would it?
For pedestrian wind comfort, the default is generally steady state. If you run other kind of things, it's not steady state anymore and is not runs anymore. For example, wind loading over structures, buildings, and high towers to see the frequency of resonance and so on. You would need to run other type of analysis. Otherwise, it would not fit the purpose.
Sure. I see a question in the chat, but I think it might be for the previous talk. How do you model viscosity Yeah, I think that's the previous talk. For the domain size, so that's automated by Helix, is it that you, or Helix, the size of the domain, like the height and the radius?
This is left to the expertise of the engineer. For this Niigata case, I use the geometry from the provided from the benchmark study and the size that they suggested. In reality, there are some guidelines, and actually here I present the results for a cylindrical domain. But there are people which prefers to run a wind tunnel and to put the cylinder inside and to rotate like the city. Let's say that in that case you have to rotate the mesh, or
Sure.
yeah, you just run the same mesh. Yeah.
Okay. Very interesting. I have more questions, but we've run out of time. So if there are more questions, people can put it in the chat or Q&A, and Salvador, you can follow up there. Thanks very much again.
Okay, thank you.
So we'll move on to the last talk. So Jan van Gorsel is our last talk in this session. So Jan, feel free to share your screen, and then you can start whenever you're ready. And just in case people don't know, on the right-hand side as well, there'll be a handouts drop-down, so you can have access to the 4 authors' abstracts if you want to look at them as well. Okay, go ahead.
Yes, okay. Welcome, everyone. I will talk about numerical analysis of broken regular wave forces on a Schall-Weinand cylinder. So I assessed the wave impact on offshore lighthouses. All these lighthouses are still used for navigational purposes, especially in the case of failure of modern navigational equipment. And most of them are over 100 years old. So also with increasing sea level rise and larger waves, there is a need to assess the wave impact on these structures, so that their structural integrity can be assessed to see how long they will still withstand these large forces. A lot of research was done. Sorry, a lot of research was done into this topic, but only for breaking waves. So in my situation, we have broken waves, which you can see here on the right. But while all the other research done, at least as far as I know, is for breaking waves. And you can see that the wave shape is very different. And this then, of course, also influences the impact on the structure, on the lighthouse, which is idealized as a cylinder. The main objectives of the study were to validate the numerical model and find the values of lambda and CS for broken waves. Lambda and CS are part of the formula to determine the impact of the wave onto the structure, where lambda is part of the water level elevation of the incoming wave, and CS is a adjustment factor for the unknown processes that occur. And furthermore, we analyzed the efficacy of mules and isolate factor for this specific situation. For the numerical setup, of course, I used OpenFOAM version 1912. And in that I used the WaveSystem toolbox by Jacobsen et al. To set up a numerical wave tank, which was coupled with Ocean Waves 3D to simulate the waves over the first 70 meters of the domain. As the first 17 meters of the domain is not interesting, Ocean Waves 3D was used, as it is a simple and quick tool to determine the water level elevation. Then at the coupling zone, at 17 meters, the wave is propagated into the domain where it hits the cylinder. We also have the relaxation zones, the inlet and outlet relaxation zones, which are there to prevent internal reflection of the wave in the domain. Furthermore, we use the turbulence model by Lossan, the stabilized turbulence models proposed by Lossan and Fuhrman to, and of course the isolate factor method proposed by Rumby et al. In 2016, and the mules solver. For the boundary conditions, here you can see a cross-section. For the slope and the bottom and the cylinder, we used a no-slip boundary condition. On the side, here on the front, so which is the front, we used the slip boundary condition because this indicates, because this represents the glass wall of the benchmark case to which we compare the results to. And on the back, which is the center line of the cylinder, we use a symmetry plane, and then we assume that the problem is fully symmetrical. For the validation of the model, so we validated the model using the benchmark case by Lossan and Jiahao in 2018. And from this benchmark case, we compared first the results of a 2D simulation for 6 different wave states, with a wave height varying between 5 centimeters and 15 centimeters, and wave periods varying between 1.2 seconds and 2.44 seconds. And this was done to assess the needed grid size in the model. Once the optimal grid size was found, the model was extended to a 3D simulation where we included the cylinder and then also compared to the forces measured in the benchmark case. Today, as we don't have that much time, I will only talk about the 3D validation, which then includes the force. The force is computed by Niels and Isaac vector and compare them to the benchmark case. Here, you can see on the y-axis the force and on the x-axis the time for the experiment, for the Isaac vector solver and the Niels solver. The first thing that you can see, this is for 15 centimeter waves, so the wave period of 1.5 seconds. And the first interesting thing to see is when you compare the peak-to-peak values, that for the experiments, the peak-to-peak values are larger than for Isaac vector. Isaac vector again is larger than Niels. Second interesting thing to see is a returning long wave in the domain, which is approximately 20 to 25 seconds. And this corresponds with the eigenvalue of the waveform. Furthermore, as we have regular waves, we can take the individual force signals from the time series and average them out, which results in an ensemble average of the force signal. Again, here on the y-axis, you see the force, on the x-axis time, where the signals are all aligned at the 0 seconds, where the peak force is aligned at the 0 seconds. The first thing that you can immediately see is the rising time. The rising time is the time to go from a force of 0 to the maximum force. As you can see, for the experiment, for Niels and for Isaac vector, there's a significant difference. But the next interesting to see is the average peak force. Although the peak-to-peak values are different, when you average them out, the difference is only 1.5 to 2 newtons. However, as this averaging process wears out the individual characteristics of the signals, we also compare the individual force, a signal for all three. As you can see, there are 4 peaks present in all 4 signals. So this first peak is due to the initial violent impact of the other body onto the structure. And the second peak is caused by the water that was first moving upwards. It's now falling downwards, creating a high pressure gradient at the toe of the structure. And this also results in a peak force. And the third peak is by the remainder of the wave that arrives at the structure. And we have a fourth peak, which is caused by the last little bit of the wave that hits the structure. So now that the model is validated, it seems to be able to accurately represent the benchmark case. We took a look at the pressure distribution caused by the force, and as I mentioned, the curling factor and slamming coefficient. For the pressure distribution, we looked at the instances of the pressure at the time of the peak force. So at this peak, and we averaged them out for all these instances, as was done for the force, which you can see here. At the top is the results for Isot factor, at the bottom is for mules. On the y-axis, you can find its location on the height of the cylinder. On the y-axis is the location around the cylinder, and of course the pressure. So with red meaning high pressure and blue is a low pressure. As you can see, all the pressures mostly focus on the first 30 degrees of the cylinder. Let's focus more on the center line, so really in the middle, where the pressure is highest. For which we have a small video. At the top, you can see the state of the wave when it propagates towards the cylinder and hits the cylinder. In the middle is the force, where the dot indicates the time step. And at the bottom, you will see the pressure in the center line of the cylinder. That also includes the centroid of the pressure and the area or the height on the cylinder that is affected by the wave. As you can see, there is a very high instantaneous peak, but also there's an instantaneous peak in the force. And if you pay close attention, you will also see that the pressure is maximum not at the peak force, but just a bit before. Furthermore, we also looked at the computational costs. We noticed that in 3D, the Isot factor solver is faster. We had approximately 1.2 million time steps, and if you take an average assumed cost of 20 cents per hour, then finding the medium time steps. So for mules, we have a time step. The time needed per time step is 9.68 seconds. For Isot factor, 8.57 seconds, resulting in approximately 645 euros and 507 euros for mules and Isot factor, which is a large difference. To conclude, that the numerical model seems to be able to compute results similar to the benchmark case for this specific situation. And these results, we found values for the curling factor of 1.25 versus for broken waves versus 0.46 for breaking waves. And we also found a value of 0.45 pi for the slamming coefficient versus 2 pi for breaking waves again. So these results are quite different. So the results between broken and breaking waves are quite different. Also the effectiveness of the solver. From these results, it seems like that Isot factor is the preferred solver for a situation like this, with being faster and better in predicting the forces on the structure. Are there any questions? Thank you.
Great, thanks very much. Yeah, that'll be. I don't think I'll ever get used to not having an applause at the end of the talks. It's always a bit weird doing it online. So I have quite a few talks. If people have questions, they can put them in the chat. I'd encourage you to do that now. So why do you think there is a difference between the models, both mules and iso advector, versus the experiments? What do you think the model is not accounting for?
The model is not accounting for that. We don't take into account compressibility of the water, although it's probably not needed in this small scale. The scale is 1/81 fruit scaling. But also there could be some post-processing in the results of the benchmark case that influence the comparison.
Mm-hmm. Yeah, that makes sense.
Especially as you could see in the rising time, that could be due to the post-processing in the experimental data.
Sure. Yeah, I guess always, if they haven't given the raw data, it's hard to know. And for the iso advector, so you're recommending for cases like this, it seems to work better. Are there any downsides in terms of robustness or stability you notice between iso-advector and mules?
No, not that I can think of the top of my mind, but we also looked at for mules in 2D, but then only purely at the speed of the simulation. But in 2D, mules seem to be faster. So that's purely for wave propagation, so not for the impact.
Okay.
Yeah.
It's nice. It's nice that you included the costs of the simulations. You don't often see people doing that, even though I know Salvatore did it before as well. It's nice to see how expensive these models are.
It puts it in perspective because
yeah. I think you can buy an okay computer for the price of each simulation.
Yeah, exactly. And although the difference in time is only 1.1 seconds, but when you have 1.2 million time steps, it accumulates, of course.
Yeah. How do you plan to use this model in the future, or is this study complete?
No, although I graduated, so I won't be doing anything further on this. But the idea is to further elaborate this model and to also look at other wave states and different slopes, because the slope will also influence how the wave breaks, either earlier or later or closer to the cylinder or not. And so that's then in the end a simple formula can be made to assess the impact on these lighthouses.
Sure. Yeah. Makes sense.
Because a simulation, it took way too long because the computational resources were limited.
Sure.
So it took 3 months to run the simulations.
Wow.
Yes. So in the end, of course, if you have a simple formula to assess the impact of such waves onto lighthouses, then you can do it like this instead of running an OpenFOAM model for 3 months.
Yeah. Well, that makes
sense.
Great.
So
there's just one comment. One comment from Petros. Very nice visualizations, Jan. Really well done. So
thank you very much.
On that point, we'll finish there. We're out of time, so there are 10 minutes or 9 minutes now of a coffee break for everybody, and then I think the first keynote will be at 25 past. So not half past, it's 25 past. So thanks very much to the four speakers again, and I'll encourage everybody to follow up with them in the meeting hub if you saw anything interesting you wanted to chat about. So thanks again, and I'll see you in the next.
Thank you, everyone.
Bye bye, everybody.